Alright, so we begin today with the fourth chapter, and the title of the chapter is the logarithm, powers and inverse trigonometric functions. We will define the complex logarithm, little log z and capital log z. We will define the power function z to the power alpha. We will prove the binomial theorem, and we will introduce the inverse trigonometric functions. Okay, this is the material that I plan to cover today. Alright. So, the logarithm. So, first the definition of the logarithm. So, given a complex number z, a number w such that e to the power w equal to z is called a logarithm of z. As we shall see, there could be several candidates for w. Why? Because if e to the power w is z, then e to the power w plus 2 pi I is also z, right? Because what is e to the power 2 pi I? Cos 2 pi plus I sin 2 pi, which is 1, right. So, exponential function is periodic with period 2 pi I. So, if one particular w works, then w plus 2 pi I k will also work. So, it is a logarithm of z, and we are going to denote it by little log z. Note that if z equal to 0, then the w does not exist, because exponential function omits the value 0. So, I have to first begin at least by assuming that z is not 0, right. So, let us assume that z is not 0, and we seek w, which is u plus iv, such that e to the power w equal to z, alright. Alright, if e to the power w is z, that means e to the power u plus iv is z, that is e to the power u into the e to the power iv is z. Let us take the absolute value of both sides. U is real, mind you, and v is real. And what is e to the power iv? Mod of cos v plus I times sin v. So, it is square root of cos squared v plus sin squared v, that is 1. So, it is a unit complex number. And so, e to the power u is mod z. So, u is the ln mod z, where ln always denotes the natural logarithm of the positive real number mod z, right. So, u has been computed now. Alright, now go back and put this value over here. Go back and put the computed value of u over here. What do you get? E to the power iv is left over, right. E to the power iv is z upon mod z. Let us call it cos theta plus I times sin theta, where theta is an argument. You could take the principal argument if you wish. Let us do that. Let us take the principal argument, arg z, alright. No harm. After all, z by mod z will be cos theta plus I times sin theta. I could take theta to be the principal argument. Then cos v plus I times sin v equals, because this is nothing but cos v plus I times sin v. The right hand side is cos theta plus I times sin theta. What does it mean? Cos v equal to cos theta and sin v equal to sin theta. So, that gives you, if cos v equal to cos theta and sin v equal to sin theta, then v equal to theta plus 2 pi k. So, we have agreed to take theta to be the principal argument, and then you are adding to the principal argument 2 pi k. So, v is one of the arguments, right. Now, since we already agreed to take to be the principal argument, let us just cancel it off. Let us just not, we have taken theta to be the principal argument, right. So, what is finally the, so if theta is the principal argument, then v is one of the arguments, correct, one of the arguments. So, we get what? Log z equal to ln mod z plus I times little arg z, because I have taken a principal argument and I am adding a 2 pi k, where k is an integer, right, where k is a integer, right. So, if I take the principal argument and add 2 pi k to it, I get a general argument, and so I get, so this arg z is multi-valued, right, arg z is multi-valued, arg z is multi-valued. So, little log z is also multi-valued, correct. If arg z is a multivalued function, then little log z is also a multivalued function. However, here if I take the principal value of the argument, then the corresponding logarithm will be called the principal logarithm. If I take the principal value of the argument and work out the logarithm, then that logarithm will be called the principal logarithm, correct? Is it clear? So, little log z is a multivalued function, correct? What is the little log z? Little log z is ln mod z plus I times little arg z. Little arg z is multivalued, so little log z with lowercase l is also a multivalued function. Now, in specifically if I fix the argument to be the principal argument, then the corresponding logarithm will be called the principal logarithm, correct? That is the definition. So, if I pick the principal value of argument, then the corresponding logarithm is called capital log. I will always use uppercase letters capital L for the principal value and the lowercase for same lowercase one for the multivalued function. So, now this is it's very clear now, the real part of logarithm is little log ln of mod z. When I use the letter ln t, ln will always denote the natural logarithm, the real natural logarithm of a positive real number. The notations have been fixed. Notations have been fixed. When I am referring to the real logarithm of 2, it will be ln 2. When I say log of 2, it is the complex logarithm of 2. What will be log of 2? It will be ln of 2 plus I times argument of 2. And the argument will be a multivalued thing, etc. Is it clear? So, do not confuse the things. Real part of log z is little ln mod z. What is the little ln of mod z? Half little ln of x squared plus y squared, right. Now, this part we have seen in chapter 2 is harmonic, and so it will have a harmonic conjugate on the right half plane. What is the harmonic conjugate that you found in those exercises? It was tan inverse of y by x, correct. It is the angle function. Tan inverse of y by x is the angle function, correct. On the right half plane, you can write the angle function as tan inverse of y by x. That formula does not hold in the upper half plane, right, because the upper half, so if you put tan inverse of y by x in the right half plane, that on the positive real axis, what is the value? 0, because y is 0, no. And as you, and what happens to points on the imaginary axis in the upper half plane? Yeah, x goes to 0 and y is positive. So, it is tan inverse of plus infinity. What is it? Pi by 2. In the lower half plane on the imaginary axis, it is minus pi by 2, correct. Now, if you go further from the positive real axis, if I start going, I come to the imaginary axis, the tan inverse of y by x has gone from 0 to pi by 2. If I proceed further in the second quadrant, it is supposed to go beyond pi by 2, correct. I am taking the principal arg, right, it's supposed to go up to pi, and here downstairs it is supposed to go up to minus pi. So, the formula tan inverse will not work, because tan inverse will always take a value between minus pi by 2 and pi by 2. When I say tan inverse of y by x, what am I doing? I am taking the real tan inverse, right. We have not even discussed the complex tan inverse yet, right. So, that will be always be between minus pi by 2 and pi by 2. So, that formula tan inverse of y by x will not hold in the upper half plane, it will only hold in the first quadrant in the upper half plane. So, if I want a formula for the argument function, the capital A arg z in the upper half plane, what is the formula? The right half plane, tan inverse of y by x, you said. In the upper half plane, what will be the harmonic conjugate of half log x squared plus y squared? In the upper half plane, what would be the corresponding thing? It will be cos inverse of x upon root of x squared plus y squared, correct? Alright. So now let us write down. So in the upper half plane, the harmonic conjugate of half ln x squared plus y squared is cos inverse of x upon root of x squared plus. Please check this. Take this as your v, calculate v sub x, v sub y. What is your u? U is half ln x squared plus y squared. You can calculate u sub x and u sub y once and for all and keep it. With this as your v, calculate your v sub x and v sub y and check u sub x equal to v sub y, u sub y equal to minus v sub x. Check the Cauchy-Riemann equations with this as your u, as your v. I had done it and it works, and I urge you to do it. In the lower half plane, what is the formula? Cos inverse of x upon x squared plus y squared will work, root. It's a I am saying that it is minus cos inverse of x upon root of x squared plus y squared. You are probably wondering, if the thing works with the plus sign, well, how can the same thing work with a minus sign? I seriously urge you to calculate the derivative of this and check the Cauchy-Riemann equations, and then you will understand why the plus sign here and the minus sign here. Please do this exercise. It's important and it's instructive and it is essential for you to understand. So now we have a funny situation. We have the capital arg z, the principal argument has three different avatars, three different expressions. On the right half plane, you say it is tan inverse of y by x. In the upper half plane, you are saying it's cos inverse of x upon root of x squared plus y squared. In the lower half plane, you are saying it's minus cos inverse of x upon root of x squared plus y squared. Now, in calculus, it is not surprising that a function is defined in different ways, right? You say f of x equal to x if x is positive, if x is greater than or equal to 0. You say that f of x is minus x if x is less than or equal to 0. This is very common, right, in calculus. But then you have to check what? If the two pieces, I say f of x equal to x if mod x, if x is greater than or equal to 0. I say f of x is minus x if x is less than or equal to 0. But then on these two parts, origin is common, right? And the definition must agree at the origin, right? Does it agree? So the function that I just described makes sense. Suppose I say f of x equal to 1 if x is bigger than or equal to 0 and minus 1 if x is less than or equal to 0, this function is not correctly defined. Because at the origin, what are you going to take? Plus 1 or minus 1? So either I have to exclude the origin from the first part or I have to exclude it from the second part. And of course, the function will be discontinuous, that's okay. I could say f of x equal to 1 when x is greater than or equal to 0 and f of x equal to minus 1 when x is strictly less than 0. That's a well defined function. It is discontinuous at the origin, but never mind. But if you define it, if you define f of x as something for x greater than or equal to 0 and something else for x less than or equal to 0, then at 0 the two things must agree, correct? So now here we are doing what? We are saying that we are defining the function to be tan inverse of y by x on the right half plane and cos inverse of x upon root of x squared plus y squared in the upper half plane. These two regions overlap in the first quadrant. Do these two things agree on the first quadrant? Is it true that tan inverse of y by x is the same as cos inverse of x upon root of x squared plus y squared when x and y are both positive? You must check. As a preliminary, let us check it at the point 1, 1. Tan inverse of y by x will be pi by 4. Cos inverse of x upon root of x squared plus y squared is 1 over root 2. It's pi by 4. It's correct. But then checking at pi by 4, is it enough? Checking at 1, 1, is it enough? you should do the checking, or you have to convince yourself that if you check it at 1 1 it is enough. You have to give a, you have to show that the two things agree on the first quadrant. What about the right half plane and the lower half plane? They have the fourth quadrant in common, isn't it? And is it true that tan inverse of y by x is the same as minus cos inverse of x upon root of x squared plus y squared? Let us do a test run. Let us take the point 1 comma minus 1. So for the first, according to the first definition, I am going to get tan inverse of minus 1. What is tan inverse of minus 1? Minus pi by 4. And according to this definition, what am I going to get? Minus cos inverse of 1 over root 2. What is it? Minus pi by 4. So I will now go ahead and say that you should check it in general, correct? So now the argument function has been defined on the plane minus the negative real axis. The plane, so I removed the negative real axis, and on the complement the argument function has been correctly defined. And on each of the pieces the function is continuous and they patch up and the pieces are open sets. If you take two functions f and g, both the functions are continuous, both the functions are defined on open sets which overlap. On the overlap, the two functions agree. That means that the two functions can be joined together. Like I can say f of x equal to, I can define the function to be f of x in the first open set, g of x in the second open set. It is a meaningfully defined function, and this will also be continuous provided both the sets u and v are open and the individual pieces are continuous. Is it clear? Should you want me to repeat this again? Take two functions f and g. F is defined on the open set u, g is defined on the open set v. F and g are individually continuous, and fx equal to gx on u intersection v. So on u union v, I can define a function. The function is f of x when x belongs to u, g of x when x belongs to v, meaningfully defined function on u union v. This function on u union v will be continuous, correct? And that is what is happening here, na? Tan inverse of y by x is continuous, cos inverse of x upon root of x squared plus y squared is continuous, both are open sets. On the overlap they agree, we have just convinced ourselves, or you have promised to verify it in general. Similarly, on the right half plane and the lower half plane, everything is working well, and so the function is continuous. Is that correct? So the argument function arg z with capital A has been analytically described in terms of x and y, and the formula takes different forms in different half planes. All right. I don't know how to do it without in one single formula, one single expression. I don't think I can do it. Maybe if you can do it, please illuminate me on this. But this is natural. I mean many functions are defined, absolute value function. How are you going to define it? F of x equal to x when x is positive, f of x equal to minus x if x is negative, right? That is the way you define the absolute value function. So it is not surprising. I mean functions are defined this way, and it is continuous. We have defined it. We have defined the argument function, capital arg z, right? Is it clear? All right. Lower half plane we have taken to be minus cos inverse of root of x squared plus y squared. Upper half plane is cos inverse, lower half plane minus cos inverse, right half plane it is tan inverse. I have to take this because just this and this will not work, no? Because then the whole of the x axis is gone. I can't just simply take the cos inverse upstairs and downstairs, because then what happens, then the whole of the real axis is gone. I don't want the whole of the real axis to go, only the negative real axis I am cutting. I still want the function on the positive real axis. So that when I put in the tan inverse business, that is also covered, correct? So is this domain star shaped? Complex, this R2 minus x comma 0 where x is less than or equal to 0. Is it a star shaped domain? It is a star shaped domain, correct? And V is continuous. I just told you, calculate del V by del X and del V by del Y and check that del V by del X and del V by del Y are also continuous. Calculation of the del V by del X, I can leave it to you. It's calculus, differentiating inverse trigonometric function of a real variable. Alright, you can do that and then check that the Cauchy-Riemann equations are satisfied. In other words, U plus IV is analytic in this domain R2 minus x comma 0 where x is less than or equal to 0, correct? So, in other words, capital log is, what have we described just now? Capital LOG, the principal logarithm is what has just been described in the plane minus the negative real axis. That's an analytic function. We are just described that analytic function, correct? In other words, V of xy equal to capital arg x plus iy. This is the harmonic conjugate in this domain, the slit plane. I am going to call it the split plane, and capital LOG is the real part, half ln x squared plus y squared plus I times capital arg x plus iy is thus complex differentiable, and since the partials are all continuous, it is actually analytic. Our definition of analytic functions is that it should be complex differentiable and f prime should be continuous. The derivative should be continuous, correct? We will come back to this definition later. I will have to make some comments about this definition and what standard, it deviates slightly from other standard definition. Now you might ask a very important question, what is so sacrosanct about the negative real axis? Why can't I just cut the positive real axis and say that the angle will go from 0 to pi? I will start measuring the angle from 0 to 2 pi. There is nothing sacred about this negative real axis, right? How does one go about doing this? One has to do it all over again. When I will have to divide, when I will have to define in the upper half plane, left half plane and the lower half plane piecewise, correct? I will leave it to you to do the things. Remember, now I can't define cos inverse of x upon root of x squared plus y squared, because this function cos inverse takes values in 0 to pi. That will work in the upper half plane. I am going from 0 to 2 pi, but that minus cos inverse of x upon root of x squared plus y squared which I used cannot be used anymore, because minus cos inverse of x upon root of x squared plus y squared will go from minus pi to 0, whereas we are supposed to go from 0 to 2 pi. So in the upper half plane I can take the definition cos inverse of x upon root of x squared plus y squared, but not on the left half plane, not on the lower half plane. You will have to come up with suitable definitions. You can do it, and I suggest you do it yourself, and I think after a little bit of experimentation you will get something like this. I mean, this is not the only way to describe it, there are several ways to describe it. So try to, okay, the exercise for you is find a analytical expression for the argument, find an analytical expression for the imaginary part, correct, for the logarithm where the positive real axis is cut, instead of the negative real axis. Sometimes you might have to do that, and again check the analyticity of the function. Don't have to write this down. I mean, you can, you understand the problem. The problem is clear. Cut the positive real axis and work out the harmonic conjugate. Just remember that and just work on that instead of writing these expressions and all these things. Right? Just do it independently and then we can verify whether, because you will get a different expression. You could get different expressions because the inverse trigonometric functions have different avatars, you know. Sine inverse can be written as cot inverse of something else. I mean, you could, and then you have various identities, right? Cos inverse is pi by 2 minus sine inverse and all sorts of things. So don't just stick to one particular expression. This is just one sample. It should work. Whatever you write should be correct. That's the point. That's all the requirement. Whatever you write down should be correct. It should be complex differentiable. Continuity should be there. on the overlap things should agree, those things, just make sure that those things are there, alright. Please do it yourself. So now you can have a function like a little log z equal to ln mod z plus I times theta z. All that is really important is that we have the angle going from 0 to 2 pi, and this angle can be suitably defined. After all, when I cut the complex plane along the positive real axis, that is also a star shaped domain. That's also a star shaped domain. So the harmonic conjugate, whatever it is, exists. I know that the harmonic conjugate exists. The exact expression is not relevant. It's not relevant because I know the harmonic conjugate exists, and I know that u plus iv is going to be analytic. It's f of z, and that's actually log z. My only interest is what is the derivative of log z. It's going to be, how do you differentiate the f of z? What is f prime of z? F prime of z is u sub x plus I v sub x, but v sub x is minus u sub y, isn't it? So throw away the v sub x and put minus u sub y, and you have the formula for u, no? The formula for u doesn't change. Half ln x squared plus y squared. Use that everywhere. So the exact expression for v is not important. What is important is that you should convince yourself that it can be done no matter which ray you cut. Negative real axis we are done, positive real axis we are done. You could cut the upper imaginary axis if you like, and then the angle will go from minus 3 by 2 pi to pi by 2. You can also write down expressions for this, that's an exercise. But again, this domain is also a star shaped domain, the harmonic conjugate will exist, and ln mod z plus theta z will be analytic, and that will be a little log, little log, and the derivative of little log, I don't care about the angle function as long as I know it exists and it is differentiable, etc., because I can use the u to calculate the derivative. The f prime of z is u sub x plus I v sub x, but v sub x is minus u sub y, finished. So I don't have to worry about u at all, v at all, I can work with u. Is it clear? Only important thing is, if you cut which ray, you must know which ray you are cutting. Are you cutting the negative real axis? Then the angle goes from minus pi to pi. Are you cutting the positive real axis? Angle goes from 0 to pi. Are you cutting the ray making an angle of 45 degrees with the x axis? Then the angle will go from here to there. You have to be clear about that. That's all. Is that clear? How to work, you should know how to work with the logarithm. Expressions, analytical expressions for v is not important. We are never going to use it. I just wrote it down just to make sure that it can be done. You should do it once. Alright. Now let us get to business. So let us take that, recall that if f equal to u plus iv is complex differentiable, then the derivative of f is u sub x plus iv sub x, but v sub x is minus u sub y. So I can use the u alone and calculate the derivative. So in the present case, I am interested in f of z equal to log z. So I use the u to do the differentiation, del x of half ln x squared plus y squared minus I by 2 del y of ln of x squared plus y squared. Now you can easily differentiate ln of x squared plus y squared. I can differentiate ln of half x squared plus y squared, and I can do the calculation, correct? And you do the calculation, what will it be? It will be x upon x squared plus y squared, y upon x squared plus y squared. So I get x minus iy upon x squared plus y squared. But x squared plus y squared is x minus iy into x plus iy. The x minus iy cancels out. What is left over? 1 over x plus iy. So derivative of log z is 1 over z, no matter which branch you choose. No matter which branch you choose, the derivative is 1 over z. So like the argument, little log is multivalued on c minus the origin, but on the slit plane it is single valued. See, multivalued, why do I say that the argument is a multivalued function? You start from a point and you go round the origin. Say suppose you take the point -1, you start from the third quadrant. What is the argument? Minus pi, right? And then you go round, come to the positive axis, go up and come down. What is the argument? Pi. So you start from a point and return to the same point. The argument has, and go counterclockwise, the argument has changed from minus pi to plus pi, correct? And so at that particular point -1, I use capital arg z. That was what? Pi was included, minus pi was excluded. One of them was included, one of them was excluded, right? So it became discontinuous function. Or I can say it is a multi-valued function, right? The problem is that suppose I cut the complex plane along the negative real axis. That means that those points are not there at all, and I can't go around the origin anymore because there is a barrier. There is a barrier, I can't go around. So there is no question of multi-valuedness, it is only single valued. Multi-valuedness will appear, the argument will become multi-valued if you are allowed to go around the origin and return to the same point. You can't do that, right? I have cut the plane along the negative real axis. So the points in the negative real axis are no longer there in your domain. So if you start at the point, you cannot return to the same point and go around the origin. You can imagine, no? I can go do something, I can do something, and try to write down a closed curve, return to the same point. This closed curve will not have 0 in the interior, inside, because you are not allowed to cross the negative real axis. Or you can cut the positive real axis. You are again prevented from going around the origin. You could remove any ray from the origin, going off to infinity. Again you can't circuit. You don't have to remove a ray. You can remove a parabola, one half of a parabola, like this. You can still not go around the origin. Some curve can be removed, starting from the origin and going off to infinity, right? So it's single. So on the slit plane, it is single valued. It is no longer multi-valued. Okay? Clear? Logarithm function is clear. It is the most basic function, because many other functions will be defined using the log, right? Next is the power function z to the power alpha. Z to the power alpha is defined as x of alpha log z. Remember, I did not write this, I did not tell you this before. Xz is the same as e to the power z. It's convenient when you have a big expression. It is convenient to write x rather than e to the power. Readability is enhanced, so there's a notation is used occasionally. And then the principle that, so since little log is multi-valued, z to the power alpha is also multi-valued, but then the principle, if you use the principal value of log, then the corresponding value of z to the power alpha will be called the principal branch. It will be called the principal branch of z to the power alpha is x of alpha capital log z. Principal value, principal branch, use whatever phrase you want, doesn't matter. Capital log z. Correct? Now, so let us take alpha equal to half. What is root z? Root z is x of half log z. Now, if I take two different values of log z, then they will differ by 2 pi I k. They differ additively by 2 pi I k. Correct? They differ additively by 2 pi I k. But what does the exponential function do? Exponential function converts the sum into a product. X of z1 plus z2 is x z1 into x z2. So the corresponding values of root z will change multiplicatively, will differ multiplicatively by e to the power I pi k. 2 cancels out, there is a half there, remember. The two values of root z will differ multiplicatively by e to the power I pi k. So, if I take two different values of root z, one of them will be different from the other by a factor of e to the power I pi k. Now, what are the values of e to the power I pi k? If k is even, e to the power I pi k is cos pi k plus I times sin pi k. Sin pi k is 0 and cos pi k is either plus 1 or minus 1. So, the two values of root, so the root z is a two valued function. It takes on only two values and the two values differ by sign. Okay? Is it clear? Alright. So, the root z is two value, correct? Exercise, find all values of I to the power I. Is any of this real? Which of it is principal? What is the principal value of I to the power I? Please do this, calculating all the values of I to the power I and identifying the principal value. You will get a surprise. Very interesting. Find all values of I to the power I. Alright. Just write down, find all values of I to the power I, that's all. Nothing, don't write the whole thing out. Now let us calculate the derivative. We have calculated the derivative of the logarithm. Now let us calculate the derivative of z to the power alpha. ddz of z to the power alpha is ddz of x of alpha log z. I am going to take the principal value and do the calculation. And remember, I underlined the capital log just to remind you that we are talking about the principal value everywhere. Everywhere I am taking the principal value. So it is, what is the derivative of the exponential? The exponential function itself times derivative of whatever is inside. Alpha is a constant and derivative of the log is 1 over z. Remember, we have just done it. So it is alpha by z into z to the power alpha. On the other hand, 1 over z is what? What is 1 over z? 1 over z is x of minus log z. Log z is multivalued, but x is periodic. The periodicity of the exponential function kills the multivalued nature of log. Two different values will change by 2 pi I k. Two different values of log will differ by 2 pi I k, but the exponential function will take the same value because exponential function is periodic with period 2 pi I. Right. So I can write this 1 over z as x of minus log z, and then again use exponential addition theorem. I can write it as alpha x of alpha minus 1 log z. Remember that this is a principal value I am writing down here. This is the principal value. So it is alpha z to the power alpha minus 1. So you differentiate the principal value, again you get the principal value. Remember, you can't take one value here and then write a different value on the right hand side. No. That's the reason why I am underlining the capital all over the place. The left hand side what you see is the principal value, right hand side is also the principal value. Our calculations confirm it. Be careful. Don't just mix up the principal values and non-principal values. You're going to get wrong answers. You have to be careful about these things. When you write such an equation, when you say that ddz of z to the power alpha is alpha z to the power alpha minus 1, I am going to ask you what is the interpretation here and what is the interpretation here. What is the meaning of z to the power alpha on the left hand side? What is the meaning of z to the power alpha minus 1 on the right hand side? Here in this particular case, principal value and principal value. That is what the calculations show. Alright. So on the slit plane, the plane slit along the negative real axis, capital log z is analytic and single valued. So z to the power alpha is also analytic in that region. Likewise, z to the power alpha has an analytic branch on the plane slit along any ray emanating from the origin. There is nothing sacrosanct about the negative real axis. You could slit the plane along the positive real axis. The formula for the definition of log will change. Log z will be ln mod z plus I theta, where theta will run from 0 to pi now, 0 to 2 pi. When you slit the plane along the positive real axis, and if the definition of log changes, the definition of z to the power alpha will change accordingly. Now the binomial theorem. The binomial theorem is a very important theorem. The power series 1 plus alpha z plus alpha into alpha minus 1 upon 2 factorial z squared plus alpha into alpha minus 1 into alpha minus 2 upon 3 factorial z cube etc. has unit radius of convergence if alpha is not equal to 0, 1, 2, 3 etc. Because if alpha equal to 0, 1, 2, 3 the series will terminate and it is a polynomial as expected, it is a polynomial. So, if alpha is other than 0, 1, 2, 3 etc., the series will never terminate and the series will have radius of convergence 1. The series has radius of convergence 1, alright. And the sum of the power, the theorem continues, the sum of the power series is 1 plus z to the power alpha, where the principal value, referring to the principal value of this power function. Namely, it is x of alpha capital log of 1 plus z. And what is the domain on which this discussion is taking place? Mod z less than 1. Clear? This is the statement of the binomial theorem, where alpha can be complex also. The power can be complex. Is that clear? The binomial theorem for arbitrary exponent. Yeah, what is the question? So, let us look at the proof of the binomial theorem. So, let little yz denote the sum of the power series. By the way, it is an exercise for you to show that the radius of convergence is 1. And let us take capital yz to be 1 plus z to the power alpha, the principal value. What about little y, what about capital Y0? Capital Y0, so when I say principal value, what is it? It is x of alpha log 1 plus z, right? And I am putting z equal to 0. So, I am going to get x of alpha log 1. What is the principal value of log 1? ln of 1, which is 0, plus I times arg1. What is the principal value of the argument of 1? 0. So, it is e to the power 0, it is 1. So, capital Y of 0 is 1 and little y of 0 is also 1, you put z equal to 0 on the power series. So, the two functions capital Yz and little yz agree at the origin, correct. Now, let us prove that capital Yz and little yz satisfy the same differential equation. Now, we have two functions satisfying a first order ODE, the same first order ODE, and the two functions agree at a point. Therefore, they agree everywhere. All right. Okay, calculation is fairly routine, but let us go through this. So, let us take little yz is this power series over here. It looks monstrous, but it is routine. You have calculated series solutions of Legendre, Bessel, etc., and these kinds of expressions are now quite familiar, all right. So, differentiate, n from 0 to infinity becomes n from 1 to infinity, term by term differentiation is valid as long as you stay within the range mod z less than 1, as long as you stay within the radius of convergence, the power series can be differentiated term by term. So, this goes from 1 to infinity, multiply by 1 plus z, you are going to get two terms, 1 into this and z into this. You multiply this by 1 plus z, you are getting two terms. Those two terms have been displayed. Now, break it up into two summations. Now, the first thing will go from the second summation has been written down as it is, n from 1 to infinity. The first summation, the index, everywhere I see an n minus 1. Everywhere I see a n minus 1. So, I will shift it to n and the sum will go from 0 to infinity. This simple technique is also familiar to you from differential equations for finding the series solutions of ODEs. So, this is n from 0 to infinity, this is n from 1 to infinity. What is the next step? Isolate the n equal to 0 term. Isolate the n equal to 0 term and then combine these two summations. Alright, let us do that. So, I have isolated the n equal to 0 term and the remaining two sums from n from 1 to infinity, all right. So, that n equal to 0 term which has been isolated has been written here. So, summation n from 1 to infinity. You see in this expression, out of this expression, this part is common. This part is common. What is not common is alpha plus n, correct? And in this expression, we have an extra alpha, right? There is an extra alpha, there is an extra n, excuse me, there is an extra n, that's, thank you. So, n minus 1 factorial, so I put in an n there. So, this n cancels out and I picked up an extra, what I left over is an alpha. Alright, so that alpha is common to both, and then if I remove the alpha, then I get n from 1 to infinity and the 0th term back again to yz. Clear? I have verified that little yz satisfies the equation, little yz satisfies this equation, this one. This has been verified now, correct? Alright. Now, capital YZ, I leave it to you as an exercise. Directly differentiate x of alpha log 1 plus z, differentiate and check, right. I am not going to do it, that is an exercise. Now, let us take the ratio. Now, we have to show that little yz equal to capital YZ. I can appeal to ODEs. I can say two functions satisfies the same ODE and they satisfy the same initial condition. So, by uniqueness theorem, the uniqueness clause in the fundamental theorem on differential equations says it all, but let us not rely on that big theorem on ODEs. Let us prove the whole thing from first principles. So, let us take the ratio little yz upon capital YZ and differentiate using the quotient rule. Apply the quotient rule, you have 1 over y squared into capital Y little y prime minus little y capital Y prime, correct. Multiply and divide by 1 plus z, multiply and divide by 1 plus z, and then you get 1 plus z y prime. What is 1 plus z y prime? Alpha y, right. Similarly, 1 plus z capital Y prime is alpha capital Y. So, you just put that down, I got 0. So, ddz of little yz upon capital YZ is 0. So, little yz equal to c times capital YZ, and so to evaluate c, put z equal to 0, but these two things are equal, they are both 1, and so c equal to 1 and little yz equal to capital YZ. Just a so we just prefer to walk that extra mile rather than relying on a big theorem on ordinary differential equations. Show that cos root z and sin root z upon root z are entire functions. What is the entire function? An entire function is a function which admits a power series converging on the whole complex plane. Cos z to the power 1/3 plus cos omega z to the power 1/3 plus cos omega squared z to the power 1/3. Is it an entire function? That is a question. Interesting question. You have to do some work. For theta belonging to minus pi open interval, find the real and imaginary parts of capital log of 1 plus e to the power I theta. And the fourth one is a problem from Macrobert's book. T.M. Macrobert wrote an old book, there is an old book actually, of theory of functions of a complex variable. There are lots of examples in Macrobert's book. Macrobert, Copson, Whittaker and Watson, Titchmarsh, these are the old classics. Number of exercises are available in these books. And this is one example. Prove that 1/2 of capital log 1 plus z squared equal to half z squared minus 1/3 of 1 plus half z cube plus etc. You have to use a differentiation theorem. Don't try to, you could try to take the product of log of 1 plus z with log of 1 plus z, but you can find the power series, you can find the series expansion for log of 1 plus z and so on, but try to do it, try to use the differentiation theorem for power series. The next theorem, I think this theorem I will quickly go through, rather I will not spend too much time explaining. Suppose omega is a star shaped domain and f from omega to c is analytic, by now everybody knows what analytic means, and fz is not equal to 0. That is, if you have a non-zero, if the domain is star shaped and the function and the analytic function is not 0, then capital log fz and fz to the power alpha are single valued analytic functions. Now, capital, now it is enough to do this, because what is the definition of this? It is x of alpha log f, correct. So if I do log f, then this follows. So now take f is u plus iv. Now I want to do I want to look at log of fz. So its real part will be ln of u squared plus v squared half. Call that capital U. In chapter 2, you have proved that this object is harmonic. So it has a harmonic conjugate. It has a harmonic conjugate V, which is not unique, but it is only unique up to a constant. The constant has to be adjusted. Okay. Anyway, the adjusting of the constant we will just set it aside. So now take that harmonic conjugate V, put them together u plus iv, and you make your analytic function capital Fz. We claim that this capital Fz does the job, that this capital Fz is the log of little fz. In other words, e to the power capital Fz is little z. That is the other way of saying it, no? Okay, so how do I check this? I have to check this, right? So now first of all, how do I differentiate this capital F prime? U sub x plus I V sub x. Now I am not interested in working with V, I am only interested in working with U. So the same trick, appeal to the Cauchy-Riemann equations and throw away the Vx and replace it by minus U sub y. Then write down, take the U expression and write down the full thing. Write down the full thing and this is what you get, correct. Again here the you have to do a little bit of adjustment with the Cauchy-Riemann equations. Again the y derivatives are gone and replaced by the x derivatives, and then the u plus iv is a common factor, so u minus iv is a common factor which cancels with the u minus iv below, and you are left with u sub x plus iv sub x divided by u plus iv. The usual calculation, you have to do the algebra and you have to check it out. Okay, I mean I can't do anything better than this. You have to verify these things yourself. This is what you get if you work out the details. So what is the upshot of the whole thing? Upshot of the whole thing is that f prime equal to little f prime upon f, correct. So now let us calculate d dz of what is f prime. F prime is d dz of e to the power fz upon e to the power fz, right. I can write f prime as d dz of e to the power fz upon e to the power fz. When I differentiate e to the power fz, is going to be e to the power fz into f prime z, chain rule, and that e to the power fz will cancel out. So so this equation can be written like this: derivative of e to the power fz upon e to the power fz minus f prime upon f. But this can be written as d dz of e to the power fz upon fz. If you clear the fractions and use the quotient rule, you will get a slightly different quotient, but that is all right, I can always readjust it. Right hand side is 0, right hand side is 0. So that means that e to the power fz is c times fz. So now if e to the power fz is c times fz, there is no reason why this c should be 1, but why is it that what would make the c different from 1? Remember fz is capital U plus I times capital V. The capital V is defined only up to additive constant. The harmonic conjugate is defined only up to additive constant. So, if we choose the constant correctly, the C can be made 1. The C can be made 1 by correct choice of the constant, and that is all, right. So, I will consider that the theorem is done. Now, let us come to the inverse trigonometric functions. Let us take a complex number a and we seek a w such that sin w equal to a. This is something that I asked you to do yesterday, but if you have not done it, then there is no need to do it because it is going to be done now. So, sin w equal to a means what? E to the power iw minus e to the power minus iw upon 2i is a. So e to the power iw minus e to the power minus iw is 2ia. So you can write this as a quadratic equation, e to the power 2iw minus 2ia into e to the power iw minus 1 equal to 0. Solve the quadratic equation, I get e to the power iw equal to ia plus root of 1 minus a squared. Now if the right hand side is 0, I am going to be in trouble because then such a w does not exist. If the right hand side is not 0, then such a w will always exist, because exponential function omits only the value 0. So now I have to examine whether the right hand side is 0 or not. So equate it to 0 and get a contradiction. Well, if this is 0, then root of 1 minus a squared is minus ia. Square both sides, 1 minus a squared equal to minus a squared. So 1 equal to 0, which is a contradiction. So this right hand side here is not 0, and so the w exists. And what is the w? Simply the log, because as soon as you have a non-zero complex number, it has a logarithm. So you have iw is log of ia plus root of 1 minus a squared. So w is 1 over root I into log of ia plus root of 1 minus a squared. Now square root is a multivalued function and logarithm is a multivalued function, and so the w is going to be a multivalued function of a. So this w is denoted by arc sin a, right? Inverse trigonometric function is arc sin a. The principal, if I take the principal branch of the logarithm here, then it will be called capital arc sin a. All right. Now, so that is the capital arc sin a is 1 over I capital log ia plus root of 1 minus a square. Right. Now, cut the complex. Is it clear how the inverse trigonometric function comes about? What did we do? Sin w equal to a. This equation was solved. Write the sign in terms of the exponential function. Get a quadratic equation for e to the power iw. So e to the power iw equal to the something, and that something should be non-zero. When you give this exercise to your students, and if their students doesn't check that the right hand side is non-zero and directly writes the logarithm, the student deserves to lose marks. Marks should be cut if the student doesn't check, and I do that all the time in IIT. Student directly writes mechanically log of 1 over I log of ia plus root of 1 minus a squared. Marks are deducted because you cannot take the logarithm without checking, just as you can't divide without checking that it is not 0. So you can't take the logarithm without checking that it is not 0. All right. So since it's a teacher training program, I want to tell you this. Now we are going to be worried about, this is a rather strange expression, 1 over I log ia plus root of 1 minus a squared. You are going to be worried about whether it is a single valued function, is a multivalued function, is it differentiable, is it analytic, what is the story? This looks like a monster. So we want to understand this slightly. What you do is you take the complex plane and you cut the complex plane along this ray and you cut the complex plane along this ray. Now I made two cuts. Is this region star shaped? With respect to which point? With respect to the origin. This region is star shaped with respect to the origin, right? So now this object ia plus, so first of all root of what is 1 minus a squared 0 here. After I cut, make these two cuts, 1 is gone and minus 1 is gone, right? So 1 minus a squared is not 0. So root of 1 minus a squared is single valued analytic because the domain is star shaped. So this is single valued analytic, 1 over I, so and then I add this ia plus root of 1 minus a squared is single valued analytic, and that again is not 0. So log of that is single valued analytic. So the sine inverse of A or arc sin A is single valued analytic on complex plane minus the two rays starting from plus minus 1 and going off to infinity. Is it clear? Okay. And you know how to differentiate the log and you know how to differentiate the square root. So, you can now by chain rule you can differentiate arc sine z. Alright, clear? Exercises. Show that arc cos z is 1 over I log of z plus root of z squared minus 1. The principal branch is 1 over I capital L O G z plus root of z squared minus 1. Does tan z attain all complex values? Determine arc tan z. This is an important question, by the way. Tan z does not attain all complex values, it misses two values. Tan z misses two values. I leave it to you to decide which values are they. Okay, and find arc tan z. And then you are asked to calculate the derivative of arc sine z. The derivative of arc sine z is 1 over root of 1 minus z squared on the domain which we have, the star shaped domain, right. On the star shaped domain you have the derivative of arc sine z. Determine all values of arc cos 2 and arc sine 1 over root. All the values. It's a multivalued function, so you have to find all values. It's multivalued for two reasons. Root of 1 minus a squared is multivalued and the log is also multivalued. So there will be two sets of values you are going to get. One for the positive square root, one for the negative square root. Show that if y equal to arc sine z, then y prime squared is 1 over 1 minus z squared. That is trivial from the previous question. But what is interesting is this 1 minus z squared y double prime minus zy prime is 0. So arc sine z satisfies this second order ODE. Y of 0 is 0 and y prime 0 is 1. Arc sine 0 is 0. Derivative is 1. So you have y of 0 is 0, y prime of 0 is 1 and you have a ODE and you can find a series solution for the ODE and therefore you will get the series for arc sine z. So this can be done. You have done series solutions of ordinary differential equations. So please do this. Find the series solution of this ODE, find the series solution of this ODE and use y of 0 equal to 0 and y prime 0 equal to 1, thereby finding a power series expansion for arc sine z. Same is the case in the next question. Show that arc sine z the whole squared satisfies the second order ODE 1 minus z squared y double prime minus zy prime and then you have y of 0 equal to y prime 0 equal to 0. So once again you can find the series solutions of the second order ODE and you can get the, thereby you can obtain the power series for arc sine z the whole squared. So these are supplementing what Professor Neela Nataraj is doing in the other part, if you like. You can take it as exercises in Professor Neela Nataraj's section. Deduce that pi squared equal to 18 sigma n from 0 to infinity n factorial squared upon 2n plus 2 factorial. Last question, question number 7. Let f of z equal to sine of alpha arc sine z. Sine of alpha arc sine z, take the unit disk mod z less than 1. Remember we cut the complex plane along those two rays. The unit disk lies in that region. Work in the unit disk, does not matter. Work in the unit disk mod z less than 1. Take the function f of z equal to sine of alpha arc sine z. It is an analytic function. Show that fz satisfies the ODE 1 minus z squared y double prime minus zy prime plus alpha squared y equal to 0, and please tell me what is this differential equation. What differential equation is this? What is it? Which is what differential equation is this? Yeah? Bessel's? No. It's not Bessel, it's not Legendre. What is it? Chebyshev's equation. This is the Chebyshev's equation. You have forgotten the ODE that you learned last month. Very sad. It is the Chebyshev's ODE. Correct? And you know how to calculate the series solution of the, excuse me please, you know how to calculate the series solution of the Chebyshev's equation. So you can actually calculate the power series for Fz. So show that, find the series solution of this ODE. Find the series solution of this ODE and deduce that sine alpha omega equal to alpha sine omega into summation k from 0 to infinity 1 squared minus alpha squared, 3 squared minus alpha squared, etc. 2k minus 1 the whole squared minus alpha squared upon 2k plus 1 factorial sine to the power 2k w. Now from this it should become very clear to you why the Chebyshev's equation has a polynomial solution if alpha is an integer. It should become very clear why the Chebyshev's equation has a polynomial solution, because it is sine of alpha arc sine z. So if alpha is an integer, if alpha is an odd integer for example, then sine of alpha arc sine z will become a polynomial, correct. So with this I conclude this lecture. This finishes lecture 5, alright. So this completes lecture 5.